Accordingly, determination of C2 value are multidimensional issue and which is hardly covers the human. So we think machine learning approach is effective and powerful tool on this subject. To input the experimental data, we designed the experimental area to survey the different conditions as shown in the figure. First of all, we make the experiment as a cross, along with the different catalyst rate and different methane O2 ratio. Then in some cases, we focus on the further detail of the impact of the flow rate and methane O2 concentration. One of the key points to determining the experimental area for survey is focusing on how to identify the peak top at the C2 value for machine learning study like this. After covering the lot of data, we selected 150 data points for the data for input of machine learning regression. And then we make the 5 different machine learning regression for the input data of 150 data points to demonstrate the C2 yield trend under the variety type of reaction condition. As shown here, linear type of regression model, LSR and SVR shows really poor scoring model. While in the case of non-linear models such as SVR, RFR, and ETR model gave a high scoring model. So we focus on those 3 type of non-linear regression model. Here I'd like to show the result of surface plot of C2 yield demonstrated by the SVR model and ETR model. What is the differences between these? And this red point represented the exact data point made by the experimental experiment in our lab. Please in mind that in the conventional view as shown in the previous slide, the methane O2 ratio impacted the shift of peak top to lower temperature. So let's see the focus on such a characteristic feature. First of all, I would like to focus on the trend in the case of SVR model. As I shown here, the SVR model did not follow the characteristic shift as a function of methane O2 ratio. Even though the methane O2 ratio was alterated, the peak tops have never made the shift at the temperature. So this regression model is not suitable for the exact situation. While in the case of ETR model, it is clearly obviously that methane O2 ratio decrease that makes the shift of C2 yield to the lower temperature. So ETR model nicely follows the exact trend of C2 value against the methane O2 ratio. I did not follow the so between those comparison, ETR model selected as the appropriate candidate for the target. So how about the RFR model? I did not show the example of RFR model. RFR model also follows the trend of shift against the methane O2 ratio. So how about the differences between the RFR model and ETR model? I would like to show the different angle of view of regression against the catalyst rate and total flow. As I shown here, ETR model follows a really good trend of the C2 alteration, but RFR model did not care the trend in part. Accordingly, RFR model gave the really good regression model. So in this case, even though the high scoring model, we have to check the detail of trend of C2 yield, and then found out that ETR model shows a really good trend of C2 alteration under the various reaction conditions. This is the schematic short summary result in part 1, experimental data-driven machine learning for catalyst understanding. We would like to propose that this approach with machine learning could potentially reduce the waste of time on designing experimental condition and optimization of reaction condition to the best performance. So machine learning regulation really good tool for understanding the reactivity for the target reaction. For the next situation, how about the literature data machine learning for the catalyst prediction? As I introduced previous slide, usually the conventional sciences refers a lot of publication in the previous, and then they brush up their imagination and inspiration and go to the achievement. But how was the machine learning application? Because machine learning follows the old trend of published the data. So if machine learning gets a great trend of data for the target, it will be the really good achievement. So we focus on the machine learning regression for the new catalyst design. From the review published in the ChemCat-Chem in 2011, we can collected 1,860 data points for published 30 years research history in the ocean reaction. We set 11 different descriptors for catalyst material, and we make a different category for C2 yield. Because the published data have a lot of bias made by the different research group and different research reactor, so we have to make the categorization of the C2 yield as is the following four different groups. Group 0 categorized 0 to 10%, and first group 1 is 10 to 20%, and group 2 is 20 to 30%, and group 3 categorized for the about 30% C2 yield. Then those data input the machine learning regression to afford a new catalyst for about C2 yield higher than 30%. There is a list of the predicted 56 undiscovered binary element supported catalysts with favorable reaction parameter on the basis of literature data-driven machine learning classification. In all cases, machine learning proposed a silica or alumina would be the good candidate for support. And interestingly, in all cases, methane O2 ratio is really small, below the 2. But this situation is really dangerous because of methane O2 easily evaporated. So we focus on how to use, how to make the validation of this predicted catalyst. At the initial stage, tentatively we selected this style of condition for the experimental validation. At that time, excluding the harmful and hard to control elements such as radium and francium, then check the experimental validation. Is this really good catalyst or not? In the real situation for ocean catalysis. Here I plotted all experimental results on the covered area in literature data. Red and yellow mark represented the silica supported binary element and alumina supported binary element. However, unfortunately, it is clearly observed that there are no desired catalysts according to C2 yield higher than 30%. In other words, cross-validation of machine learning methods gave a really good scoring model, but the machine learning prediction was not satisfied for our demand. So we interested in the reason for why machine learning regression cannot make a really good catalyst. So one of the reasons I'd like to simply show the reason here, we made a regression model along with a lot of data, and then it makes a high scoring model. But please focus on the outlier data model. After the revision of this plot, we found that this outlier model made by the high scoring C2 yield higher than 30%. So in other words, this area did not follow the machine learning regression. So that's why prediction is not overhead. After revision of the original literature dataset, we found that those high scoring of C2 yield made by the special skill of a unique reaction situation. So this unique character did not follow the machine learning regression. So in the part 2, literature data-driven machine learning, we can identify the problem. Construction of high accurate machine learning model did not contribute to revealing the rule of significantly active catalysts. In other words, direct prediction of outlier is not easy way on the basis of catalyst informatics. While I already shown the positively based on machine learning prediction, in the part 2. Machine learning and data management can reveal the trend of data. So how does a research scientist can use these tools more effectively is still a persistent subject. So let's go to the third part, high throughput screening data-driven machine learning prediction. One of our collaborators, Professor Tanike, just already constructed the schematic high-throughput screening machine. Such machine can easily take the ocean catalytic feature under the variety reaction condition. So we use this high-throughput screening dataset. Today, I introduced the prediction of machine learning, but previously we already have a publication on the basis of high-throughput screening data by using the data management. For example, after the graph theory application of pattern analysis, we can easily understand the networking, the connection, and the similarity of elements. So if you have interest for data management, please follow this publication. Today, I would like to introduce machine learning prediction on the basis of high-throughput screening experimental data. Professor Tanike already have two different publications. One is a sodium tungsten supported silica, another is a randomly selected 3-element supported catalyst. These data collected by the high-throughput screening experimentation already been open source on our platform. So for the next interest subject, how can apply the open source high-throughput screening dataset to machine learning prediction? I already have two different publications. One is focused on the methane O2 ratio is 2, O2 rich condition. Another focus on the O2 lean condition. Today I'd like to introduce the achievement of this subject. On the basis of high-throughput screening dataset collected at methane O2 ratio 6, it is already clarified that there are a lot of novel catalysts for the C2 selectivity higher than 80% with appropriate C2 yield higher than 11%. I listed as the top 10 novel catalysts for OCM under the O2 lean condition. So for the next target, how to improve those reactivity more higher C2 yield. Our final target, higher C2 yield higher than 30%. So next target, how to select the appropriate promoter as a fourth element under the O2 lean condition. So we make this style of approach. First of all, support vector regulation was implemented on the 40%. Then we make the really good high scoring model of SVR regression. This score is 86%. After that, at the SVR regression model, we selected we focus on the methane conversion value higher than 44%. Then count up the frequency appearance element at high methane conversion value. Because we would like to emphasize the activation of methane molecule under the O2 lean condition, so we wonder that addition of high frequency appearance element at this area is one of the good scenario for the next research. Obviously, manganium is selected as a promoter. So this research focuses on this style of experimental variation. First of all, on the basis of high-throughput screening experiment, we selected the top 10 catalysts. And then on the basis of machine learning regression model, we selected the promoter as a manganium. Then check the reactivity for the exact situation of ocean. Here, I'd like to show the best C2 yield as prepared 10 catalysts with and without mangan promoter. As you can see, 4 categories show the positive impact made by the manganium. potassium, vanadium, molybdenum supported BaO, lithium, molybdenum, neodymium, zirconia, lithium ion, barium, lanthanum oxide, and lithium, barium, lanthan supported lanthanum oxide shows a positive impact made by the mangan. And also, after the modification of loading amount of mangan from the 0.8% to 5.8%, it is obviously achieved that lithium ion barium supported lanthanum oxide shows a significant achievement with C2 yields of 60% and C2 selectivity with 88%. This value is really significant because as well known, the sodium manganese silica shows 15% C2 yield with 70% C2 selectivity under the present condition. And also, second, lithium barium lanthan supported lanthanum oxide also have a good performance for the C2 yield 40% and C2 selectivity 70%. So for the third category, we focus on the target on the basis of high throughput screening data and make a regression model and cut up the performance, how to improve the methane conversion value. We focus on the manganese, and manganese promotes the improves the performance for the C2 yield, and this is a really good catalyst in compared with the conventional sodium mangan tungsten catalyst. So, today I introduced our recent research progress on data-driven machine learning approach for assistance to understand the ocean catalysis and design of undiscovered cation literature data, and also catalyst modification based on machine learning assistant. On the basis of my experiments, the cross relationship between the conventional scientists and machine learning engineering is really crucial factor for the successful story on the basis of machine learning regression and machine learning prediction for the next generation of catalyst design. So thank you for your kind attention, and if you have more interest, please visit our research web. We have a lot of publication, and we also have we also promote open discussion. So thank you for your kind attention.
Thank you, Professor Nishimurashima, for the wonderful information regarding the machine learning on oxidative coupling of methane. Now the session is open for the question. I have a couple of questions. One is in the machine learning data, you have optimized the methane to oxygen ratio of 1.25 to or below 2. But then when you apply for high throughput, you are using methane to oxygen ratio of 6. So how the data is comparable with that, and why the choice of more methane there? Yeah.
Now, this stage, machine learning did not care the dangerous situation because the methane O2 ratio quite low. That makes the problem for evaporate. So for safety, we did not try to use such situation. So, but for the just checking what is the potential catalyst, just we can survey under this situation. But unfortunately, just under that situation, even though under the methane O2 ratio 3, we could not find the significant highly active catalyst. So machine learning prediction is not working well.
So another thing, like you are using manganese sodium tungsten on silica. So what is the active species? Because manganese you mentioned is a promoter. Then what is initial CH activation in which sites is it able to understand with the help of the machine learning? The reaction mechanism, my concern is whether reaction mechanism can be followed with the help of the machine learning
Yeah, thank you for such a question. First of all, the rule of manga pneumo and rule of tongue state is still under the discussion made by the lot of research group. But they focus on the redox of tungsten is one of the key for the OCM, and the mangan supports the redoxability of tungsten. And sodium also have a promoter for the production of radical, CH3 radical formation. For how to use the machine learning for the understanding the mechanism is still difficult. Because for the mechanistic study, we have to use a lot of kinetics study, but the number of kinetics study is really we have to input the data of kinetic study, but it is very difficult because we could not determine the all intermediate in the experimental situation. In the case of OCM, gas phase reaction is also key for understanding the whole mechanism, but determination of radical in the gas phase is really difficult. So that is I think the
Yeah, I understand.
not working here.
Yeah, that's fine. And one more last question. What about C3 selected? Whether are you exclusively looking for C2 or what about C3 component? Because C2, C3 both are important with respect to the value. How about the C3? Because you are not discussing anything about C3 component.
Yeah, just refocus on the C2 product. But in realistic, in experimental situation, there are some peak appearance derived from the C3 compound. Yeah. But we did not focus on the C3 compound yet.
Is there any other questions? Lawrence? So, no other question. I will take the opportunity to thank Professor Mishmura for joining with us and taking the valuable time and sharing the recent technology that is how the machine learning and high throughput is coupled. You can understand the reaction mechanism in the material aspects. So thank you once again, Professor Mishmura.
Thank you, sir. Now we'll have a short break for having breakfast. Participants who have not had breakfast yet are requested to go to the Narmada block and have their breakfast soon and be back here within 15 minutes. Please stick to the timeline and be back here in 15 minutes.
No.